in most cases, when a child is born, you can look at it and you can say, oh, what a cute little boy, what a cute little girl, whatever. Versus your secondary characteristics are the events of puberty. So, to be more specific here, because one would assume that if you have testosterone, you develop male parts, and if you have estrogen, you develop female parts. Well, that's incorrect. What happens during embryogenesis is if you have testosterone, you develop male parts, and if you lack testosterone, you develop female parts. So it's literally the presence or absence of testosterone that determines what happens to the development of an embryo, a boy or girl. Estrogen doesn't play a role here. Now we'll talk about this in more detail than you'll want to next semester. It's actually very fascinating, but to just give you the quick nutshell version, so if testosterone is present, chances are you're a male, not necessarily. If testosterone is absent, chances are you're a female, not necessarily, but in most cases. There are three structures, and I'll spare you their names for now, but one of the structures develops into the glans penis or the clitoris. So in other words, those are homologous structures. Item number 2 develops into the shaft of the penis or the labia minora. So those are, again, homologous structures. And item 3 develops into the scrotum or the labia majora. So again, homologous structures. And we'll talk next semester about all of this happens, how all of this happens, as well as the internal apparatus. But so again, when you're very, very young, when you're an embryo, you either have testosterone or you don't. If you have testosterone, these three, they're called indifferent structures. So if you have testosterone, these three indifferent structures develop into these three male parts. If you don't have testosterone, the three indifferent structures develop into what we would call female parts. The next role of testosterone or estrogen is puberty. Your secondary sex characteristics are the things that happen during puberty, and I'm quite sure you're familiar with puberty, so there's no reason to discuss that. We could add here the menstrual cycle. Of course, obviously, we're talking about females in that case. And then the last thing to put on the list for now, again, a lot more next semester with all of this, is that testosterone and estrogen stimulate osteoblast. You know a little something about osteoblasts from having put together your histology books and looking at the tissue of, or the slide of bone tissue. But osteoblasts are bone-forming cells. Literally, okay, there's a bone. The movement of calcium from your blood to your bone is driven by osteoblast. The movement of calcium from your bone to your blood is driven by osteoclast. So in the world of bone cells, we have the clast and the blast. Now in the DVD, when I show you the bone tissue and what's the little capsule where the bone cells are found? A lacuna. And I call those cells osteocytes. An osteocyte is basically a mature osteoblast. But literally, you're constantly, always exchanging calcium between your blood and your bone. That's why fractures heal, people. If I take, it's vanished. If I take this and I break it in half, nobody in the room thinks it will grow back together. Well, why will a bone grow back together? Because the calcium in your bones today will be removed and replaced with new calcium that you consume in your diet. There's a constant turnover of calcium. Literally, calcium and bone are kind of like talking about glucose and glycogen. You store your glucose as glycogen in your liver and your muscle. You store your calcium as bone. Stimulating these osteoblasts, we have testosterone, estrogen, thyroxine, another hormone that you've heard of from putting together your histology books. You know all about the follicle cells and the thyroid gland. And even a fourth one called growth hormone. Now we got into a little bit on Wednesday of last week, being too thin, body fat too low, cholesterol too low. Remember that? So here's where all of that comes up. If you're too thin, body fat's too low, cholesterol's too low, you won't have adequate testosterone or estrogen, you won't be stimulating your osteoblasts. You're still taking calcium out of your bone. Well, if you're taking it out, but you're not putting it in, what happens? Okay, fractures? Yeah. So if you're taking it out and not putting it in, you'd have a decrease in bone mass. Stated differently, a decrease in bone density. You can be 20 years old and have osteoporosis, just like an 80-year-old. And again, when this came up a little bit on Wednesday, I'm just adding a little bit to it now with the osteoblast. What happens is, you think about races that are won or lost by the 100th of a second or some crazy thing like that. I mean, it's not going to make any difference to most people in this room. Of course, I don't really know you. Some of you may be darn near professional athletes. But in most cases, it doesn't matter. But when you have professional athletes, and really all I can speak to are runners, they can quote how many seconds or half seconds, whatever, they can shave off a mile by taking an ounce off their shoes. And this is why these people have one type of shoe that they train in, called a trainer, and another type of shoe that they race in, called a racing flat. Well, if you can take, a fraction of a second off per mile, and you're running 6 miles, maybe you can take a second off your time. Second off my time wouldn't matter at all. Still be at the back of the pack. But if you're a professional athlete, where races are won and lost by 1/100th of a second, this becomes huge. And so somebody says, I'll just lose a couple pounds. And they see their 10K time or their marathon time or their 5K time improve. I'll lose a couple more pounds. And it becomes a vicious cycle, becomes basically an addiction. When the bones begin to break, what we have are often simply pathological fractures. That means the bone just broke. There was no reason for it to break. Well, it broke because it was weak, and it's weak because you're not stimulating your osteoblast. But there was no stress consistent with the breakage. You're walking across the parking lot one day and your bone breaks, a bone in your foot breaks. very similar to a pathological fracture, but slightly different cause, is a stress fracture. Clearly, stress fractures are caused by stress. Now, if your bones are weak, you're more susceptible to stress fractures. But if the bone breaks without stress, again, walking across the parking lot, just not really doing anything, that would be a pure pathological fracture. But in the stress fracture, there was stress to cause the fracture. Stress fractures don't always go with osteoporosis. A stress fracture could occur because, let's say one of you is in excellent physical condition. You bike and you swim. You have no problem at all going to the gym and swimming a couple of miles 3 or 4 days a week. You don't think anything about a 50 to 100 mile bicycle ride. You're in excellent physical condition, but you don't ever run. And your friend says, hey man, you want to do 20 miles with me Sunday afternoon? You're in great shape, man. You'll have no, yeah, sure, I'll do it. And you do it, but what's the problem? Your bones, your joints, your tendons, your ligaments, none of those things are conditioned for that. So your foot breaks. That would be a stress fracture. Right, our next hormone or steroid is cortisone. Oh, by the way, and let me just see this, because I've alluded to histology a couple of times. We will be in histology on Wednesday, so make sure you have your histology books with you and a Sharpie. There will probably be things that you want to label in your pictures, things that you want to add to all of the work that you've done. I won't cover much of what's in the supplement or the slide box document or the DVD. I'll be adding to all of that, so it's critical that you've done all that preparatory work. So we'll talk about cortisone simultaneously with the next group of hydrophobic molecules. Those are prostaglandins. And we'll do it that way because with regard to one function, they're actually opposites. So let's do it like this. So cortisone, first function, functions, I guess we could say, and then this is just repeating something from Wednesday, to stimulate gluconeogenesis. Cortisone will also stimulate, just not as significantly, glycogenolysis. And again, that you have that from Wednesday when we talked about the G words. Okay, so now, as we continue with cortisone, we'll do it in sort of a chart form, contrasting cortisone with prostaglandins. So this story starts with an injury. Maybe you stepped on a piece of glass. Maybe you were hit in the shoulder with a 2x4. Don't know why that would happen, but maybe you fell down and hit your knee. Prostaglandins stimulate inflammation. You might call it swelling. It's uncomfortable. The basis of inflammation is twofold. Something called vasodilation occurs. Now, think about what dilation means, just like your pupil that dilates and constricts. So vaso is vessel, so this is dilation of your blood vessels. So your blood vessels dilate, okay, they get bigger. This increases blood flow to the injured area. Again, draw from histology. Why would you want an increase in blood flow? Well, you've got red blood cells carrying oxygen. All of your tissues always need oxygen. But if tissue's been damaged, it really needs oxygen. You have white blood cells that fight infection. The thing is, the injury's not inside a blood vessel necessarily. In fact, your blood vessels are just what your blood cells do to travel from point A to point B. Your blood vessels are kind of like the interstates in the United States. None of you live on the interstate, eat on the interstate, sleep on the interstate. You use the interstates to travel from point A to point B, whether it's one end of Colorado Springs to the other, or whether it's Colorado Springs to Miami, Florida. But you get on and off the interstates, and what do you use to get on and off the interstates? Exits. Exits. So all over the country we have exits where we can get on and off the interstates. Our capillary beds are to our blood vessels what the exits are to the interstates. Things move in and out of our blood at the capillary level. Again, just think about histology. Think about simple squamous epithelial tissue. Think about gas exchange. Oxygen doesn't perfuse out of a great big blood vessel in your tummy. Oxygen moves out at the capillary level. Simple squamous, the very thin tissue. Oxygen moves out of the blood into the tissue. CO2 moves from the tissue into the blood. So, we increase the diameter of the vessels to send more blood to the injured area, but we also increase capillary permeability. Increase capillary permeability. That allows more stuff, we'll call it in quotes, to move out of the blood. Sending the extra blood to the injured area doesn't do any good unless we can get the oxygen out of the blood, get the white blood cells out of the vessels. So this inflammation that we know of as, oh God, man, that hurts. Ugh. It's actually good. It's healthy. It's necessary. It's step one in healing. Hold on to that, because with that, in a minute, we'll want to talk about, should we race to the medicine cabinet to take the aspirin or the ibuprofen? It's kind of like, should you take medication to stop a fever or stop diarrhea? We'll get into all of that in a minute. So this is step one of the inflammatory process, or this is the inflammatory process, step one, step two. Okay, the inflammatory response occurs. You're sick of it. Well, now your body should release cortisone. Cortisone inhibits inflammation. It does that simply by reversing these two events. So cortisone causes vasoconstriction. And cortisone causes a decrease in capillary permeability. Most of the time the system works well, no problem. Sometimes it doesn't. Sometimes you might go see a physician and have a joint injected with cortisone because it just doesn't get any better. The cortisone injection is designed to break the cycle. This could be anyone had a cortisone injection? They work wonderfully or they don't work at all. It's kind of maddening. They work wonderfully or they don't work at all. But you're delivering the cortisone right at the spot. again, to try to break this cycle. Now we have a category of drugs. We'll just talk about over-the-counter drugs. We won't get into prescription drugs. These drugs are non-steroidal anti-inflammatory drugs. Cortisone doesn't go on this list because cortisone is a steroid. And cortisone, of course, is not over the counter either. Non-steroidal anti-inflammatory drugs. These drugs inhibit inflammation by inhibiting the synthesis of prostaglandins. Okay, the very molecules that cause the inflammation. These drugs but they slow down, they inhibit the synthesis of the molecules that cause the inflammation. Well, that seems like a wonderful thing to do. I've got inflammation, I don't like it, it hurts. Let's take a drug that stops the synthesis of the molecules that are responsible for the inflammation. And again, there may be nothing at all wrong with that. But I wonder if you should take the anti-inflammatory immediately, or if it might be better to let the inflammatory cycle occur if it's part of the healing process. Well, I don't know. We can debate it and talk about it from now to the end of time, and we still won't know. But it's worth thinking about. Just like the fever. Or what about vomiting? Yeah, what about icing? What about vomiting? Should you take something to stop the vomiting, or should you let the crap get out of your system? Think about it. What about diarrhea? Should you take something to stop the diarrhea, or should you purge whatever's in there causing it? Interesting to think about that. What happens is we live in the real world. I have 40 people out in the hall waiting for me to give a lecture. I can't just not come in because I have diarrhea, so I would take something to stop the diarrhea. I can't excuse myself 4 times over the course of an hour and 15-minute lecture, so I would take that. That's the world we live in. How many times can you call in sick for diarrhea? So that's the world we live in. So we take drugs to lower fevers. We take drugs to stop nausea. We take drugs to stop vomiting. We take drugs to stop inflammation. How about the ice? Ice does the same thing cortisone does. What's funny is heat does what prostaglandins do. What does every vacationer in the United States of America who comes to Colorado for their annual ski/snowboarding vacation demand that their condominium have? Hot tub. Hot tub. And that's the worst possible thing they could do after a day on the slopes. What should they have in their condominium rather than a hot tub?
Ice bath.
Ice bath. Just like you see in the locker rooms of professional athletes. Is it fun to hang out in the ice bath and maybe have a cold beer? Probably not. But that would be the healthy thing to do. Again, think about this stuff, people. Just think about this stuff. I also want you to be aware of what the anti-inflammatories are that you can buy without a prescription. And first of all, this is not one. Acetaminophen, of course, goes by the name brand Tylenol. It is not an anti-inflammatory. It is a painkiller. There are 4 anti-inflammatories: aspirin, ibuprofen, ketoprofen, and naproxen. drug market is huge. It's a multi-billion-dollar industry. We don't have to be talking about drugs for Alzheimer's disease or high blood pressure or whatever. This by itself is a multi-billion-dollar industry. If there are only 4 anti-inflammatory drugs without a prescription, how come if you're looking at them in the store, you see 100 or maybe 200? I don't know, I've never actually counted them. But take a look at the painkiller section at King Soopers. Why do you see so many? Well, what brands does ibuprofen come under? Motrin, Advil, Nuprin, and they all say they're the best, right? Who's seen the commercial? Motrin is it is not clinically proven to be better than Nuprin. It is a lie. It is a lie. They are all absolutely identical. Okay, they come round, they come oval, maybe they come square, they come solid, they come liquid, they come hard, they come soft, they come in gel caps. But it's all the same frickin' thing. Every single pill you buy like this is exactly 200 milligrams. Unless you're buying stuff for children, okay, well then you have lower doses. They are absolutely identical. It is the biggest racket in the world. So you have multiple brands of everything. The other reason you see so many is acetaminophen gets mixed with these others. And another reason you see so many is caffeine gets mixed with these. Caffeine potentiates them. Excedrin, the greatest thing in the world. There's nothing magical about Excedrin. Read the bottle. We've had this discussion. You've made a pact to yourself to never, ever put anything in your mouth that you don't read the label on. Excedrin is nothing but acetaminophen, aspirin, and caffeine. I told you the first time I told you that. Who's gone out in the middle of the night in a blizzard to buy Excedrin? When all you had to do was open the medicine cabinet, take an acetaminophen, take an aspirin, and drink a cup of coffee. It's a racket, people. It is a racket. You are going into healthcare. Make sure you are not medically illiterate like most of the world is. That's not to say they're stupid. They might be rocket scientists, but they're medically illiterate. You will not be. You will advocate for yourself. You will read labels. You will question your physician. One more function for prostaglandins, or maybe 2 or 3 more, we'll see. Prostaglandins stimulate contractions in smooth muscle tissue. Smooth muscle is the muscle found in the walls of hollow organs. So this could be your stomach, your uterus, your small intestines. Another function of prostaglandins, and this one takes us back to aspirin. Prostaglandins stimulate hemostasis. Don't misspell that word because the word is not homeostasis. Homeostasis is that word in chapter 1 that we haven't discussed yet. This word is hemostasis. Anybody know what that means?
Regulation of the blood.
Yeah. better working definition, it means blood clotting. Blood clotting. I said this will take us back to aspirin. I want you to think about your mother, your father, your grandma, your grandpa, an aunt. You must know someone who is on what is called aspirin therapy, where they take a low-dose aspirin, I believe it's 82 milligrams every morning. The purpose of the aspirin therapy is it decreases your prostaglandin level, making it more difficult for your blood to clot, decreasing the chances that you get a clot. Remember those little vessels we looked at in the heart last week when we were talking about coronary artery disease? How easy is it to have a clot block one of those vessels? Especially if the vessel is 60% clogged with plaque, fat, cholesterol. So the aspirin therapy decreases the likelihood of a little clot forming and blocking one of those little vessels in the heart or in the brain. So this decreases the chance of a heart attack or a stroke. Okay, so I hope you see now, as I mentioned, instead of just talking about lipids, fats, and oils, by talking about all of these hydrophobic molecules, we get to talk about some very interesting molecules with some very interesting functions, things that would never come up if we just talked about lipids rather than all of these other hydrophobic molecules. So it's time to go back through these and pick up the structures. You might want the chart handy so you can refer to it. That word's probably just going to be in my way, so. Okay, so with lipids, as you can see in the chart, we combine glycerol. Notice glycerol has 3 hydroxyl groups. Glycerol is a triol. We combine glycerol with fatty acids. And you can see that in the chart. You know, you can attach 1, 2, or 3 fatty acids to the glycerol molecule, forming a mono, di, or triglyceride. Fatty acids have the carboxyl group and a hydrocarbon chain. So I don't like that noise any more than you do. Yeah, I'm weird. So we're going to attach, in this case, 3 fatty acids to our glycerol molecule. Again, check the chart. It will tell you that the reaction occurs between the hydroxyl group of glycerol and the hydroxyl component of the carboxyl group of the fatty acid. There's actually 2 ways this can occur. We can take the entire hydroxyl group off of glycerol and the hydrogen off of the hydroxyl portion of the carboxyl group. That would give us H2O. But we can also do it this way. We can take the entire hydroxyl portion of the carboxyl group off the fatty acid and take just the hydrogen off the hydroxyl group on glycerol. That will also give us H2O. It happens both ways in the body. Don't know which way you're doing it, so well, hang on, let me see how I did that. Okay, so then as a product, This, of course, is dehydration synthesis. What is it if we go to the left? Hydrolysis. We did look in the last week in the context of fat versus oil at the hydrocarbon chains. Remember that in the fatty products, largely animal products, the hydrocarbon chains are saturated, meaning no double bonds. In the oils, the more plant material, we tend to have a double bond or several double bonds, and you get into your mono versus poly unsaturated. Okay, the structure of cholesterol and the steroids. Extremely similar. That is, the three steroids that we've discussed and cholesterol look extremely similar. It's a great example of specificity and receptors in your body. The generic structure for cholesterol and the steroids, no matter which one we're talking about. There are 4 rings. 3 of the rings are hexagons. And one of the rings is a pentagon. Again, it's an excellent example of specificity. If we take a look at this, these pictures are straight out of your textbook, but imagine, guys, you have a receptor in your body that can recognize estrogen versus testosterone. The males and females, we all have estrogen and testosterone. The male has less estrogen than the female. The female has less testosterone than the male. But we all have both, and we all have receptors for both. And quite literally, the receptors in your body that bind estrogen are not the same as the receptors in your body that bind testosterone. That's how specific life is. And we don't have cortisone in this picture, but it looks the same. Very, very tiny difference. Okay, our last group of biological molecules are proteins. So the first thing on your notes, page 12, letter A, functions. With regard to functions, I want you to write down 2 words: diversity and abundancy. I want you to think about the functions that we gave carbohydrates. Energy. That's about all I said about it. That's about all there is to say about it. Yeah, we threw plant cells in there and the cell wall, the cellulose. There's really nothing else to say about it. I didn't give fat any function at all. I assume you read the book and got some functions from the book. I mean, if you want to jot some down, I'll throw them out. Flip back to the fat page and I'll throw some functions out. Energy, that's a huge function of fat. You know, any animal that's not a human stores its energy as fat. Think about the elk or something. They spend the entire spring, summer, and fall eating to build up their fat reserves so they can survive the winter. Shape of our bodies is another function of fat. Insulation is a very important function of fat. I know, for example, that polar bears measure their body fat. They don't actually, excuse me, you mind if I measure your body fat? Oh, yeah, please do. They measure it in inches. We're talking like 4 to 6 inches of body fat under the skin of a polar bear. That's how they, are comfortable in the winter. Cushioning, padding, that type of thing is a function of fat. Anyway, there's just a few. Proteins, functions, diversity and abundancy. We could start with this young man and let him give us a function of a protein. And even if he's guessing, I bet he's right. We could go all the way around the room, and everybody would have a correct answer, even the people guessing. Some of your functions might be vague, like saying enzymes, and of course, how many enzymes are there in the body? Millions. Glycolysis, Krebs cycle. You got to make all the proteins, and just millions and millions of enzymes. Somebody could say antibodies, which of course we produce when we've been invaded with a microorganism, and the antibodies kill the microorganism, so we get well. So again, some of you might have sort of vague, general examples, and then somebody else might have a specific example, like insulin or hemoglobin. So draw from what you learned in Biology 111. Draw from what you've read in Chapter 2 of the A&P book. Draw from just life. Give me 2 proteins that you see on a bottle, not every bottle, but bottles of hand lotion or facial lotion. Collagen and elastin. Collagen and elastin. Oh, better write them down. And of course, the opposite of insulin, this from histology, pancreas, islets of Langerhans, blood sugar regulation, insulin and glucagon. And if you didn't get it from histology, you certainly got it from me Wednesday in this room when we went over the G words. What's another protein that kind of fits with these? It's hair, nails. Keratin? Biotin? How about, here's a good one. Biology 111. What are these little, what's that versus what are these little things? Cilia? Flagella? What are they made of? A 9+2 arrangement of microtubules. What are the microtubules made of? What protein? Tubulin. Because we could do this for the rest of the semester. There are millions and millions and millions of proteins in a single cell. Take any cell out of your body. Inside that cell, there are millions of different proteins. I don't mean there are millions because there's a million molecules of insulin. No, I mean a million different proteins in that one cell. Human semen or ejaculatory fluid has over 10,000 different proteins. Nobody on earth knows what they do. Next semester I'll tell you about 3 or 4 of them. Nobody on earth can tell you about more than maybe 6 or 8 of them. Why are they there? I don't know. Who are you going to ask? Let's check the owner's manual. Somebody text God, somebody text Darwin. See what they say. Huh?
You actually have a manual?
Oh, you haven't seen this?
No.
Oh, I'm sorry. Yeah, I pull this out frequently. This is your owner's manual. Look at the inside. Guys, you have to remember, we're not like the lawnmower or the washing machine where somewhere there's an engineer who designed it. He can tell you the function of every little screw, every piece of it. We're not that way. We've been figuring it out since the beginning of time. We have Grey's Anatomy, the Bible of Anatomy, not the TV show. We have Guyton's textbook of medical physiology, which I've already quoted. You have it in your lecture notes. And we're still figuring it out. Yeah, I thought I'd shown you this way back. I pull that out from time to time to make my point. All right, so again, we could do this forever and ever and ever. Make sure you're familiar with a bunch of different proteins. Let's add a few more. Where did I put to our list? Receptors. These receptors could be for hormones. These receptors could be for self. What's going on when someone needs a kidney or a lung and they're trying to find a donor? They talk about, a match. Well, every cell in your body, my body, whoever's body, has a set of proteins on the surface. And your surface proteins are unique to you. Mine are unique to me. When a cell makes its way into my body that has a different set of surface proteins, my immune system says, attack, destroy, kill. And that's the basis of your immune system. When a microorganism invades your body, somebody coughs or sneezes on you, or you touch this and then you stick your fingers in your mouth. You transfer some microbe into yourself. And your immune system says, that's not Larry. He doesn't know what it is. It's self or non-self. Your immune system says, non-self, attack, destroy, kill. Well, the same thing is happening if you need a liver transplant or a kidney transplant. You're comparing the cell surface proteins on potential donors to the recipient. These proteins, by the way, are called your MHC. We could talk about membrane-bound proteins. We could put receptors on that list. We could put something like pumps. Can you think of a pump? It's a membrane-bound protein, a protein embedded in cell membranes. That's a pump. But you've all heard of the sodium-potassium pump. But you've all heard of proteins that form little hydrophilic channels to facilitate diffusion. Because we could do this forever and ever and ever. Under functions of proteins on your notes, the first two words should be diversity and abundancy. And as you know, your DNA contains the magical code to synthesize every protein found in your body. The monomers, of course, are amino acids. Amino acids are an excellent example of minimizing what you have to memorize. So the word amino tells us amine group, which is NH2. And if you think about your functional groups, which functional group is found in acids? Carboxyl group. We know that biochemistry is a branch of organic chemistry, and we know that organic chemistry is carbon-based, so I would bet that these two functional groups are attached to a central carbon. So to draw an amino acid, we start with our central carbon. We put one of these groups on the left and one on the right. It does not matter which you put on the left and which you put on the right. Give that bond a hydrogen. And you all know there are about 20 different amino acids. The thing that makes one amino acid different from another is what is attached right there. So we generally put an R there, call that the R group. So we have 20 different R groups giving us 20 different amino acids. If you check the chart, you'll see that the bond, peptide bond, that we use to put two amino acids together involves dehydration synthesis, whereby we take the hydroxyl portion of the carboxyl group, one of the hydrogens of the amine group. So we create a new bond between this carbon and that nitrogen. I'm going to condense this now and just call it NH2. So this would be our dipeptide. Recall that proteins have multiple levels of organization or multiple structures, depending on how we want to say it. The first level of organization, or the first structural aspect in proteins, is called primary. And that's simply the sequence of amino acids. So if we have a chain of 100 amino acids, which amino acid is in position number 1, which amino acid is in position number 2, etc. And again, think about the genetic code, or the DNA that forms your chromosomes, contains the code to synthesize all of the millions of proteins that your body has to be able to produce. As the sequence of amino acids is being assembled, the chain typically coils or folds. Of course, you know this one is the alpha helix. What's this other one called? Anybody remember?
Beta.
Thank you, because I couldn't think of it. Beta pleated sheet. Then we get some more complex folding. When I used to teach Biology 111, I would tell students, picture the linear sequence of amino acids, the primary structure as a wire. And then you take the wire and you coil it into a coil spring on the car, or you coil it into a slinky. That's your secondary structure. Now take the slinky and tie it in a knot. That's your tertiary structure. So we've got this coiled thing that's now folded. maybe it has some areas of coiling, some areas of pleating, and then some more coiling. Remember, 3 dimensions. This stuff is perpendicular to the plane of the board. Think about receptors, locks and keys, enzymes and substrates. Use your notes if you need to here for a second. Or if you just want to test yourself, don't use them. The disaccharide maltose is made of 2 molecules of glucose. The disaccharide lactose is also made of, is made of a molecule of glucose and a molecule of galactose. Glucose and galactose are both aldoses, and therefore their geometry is, here's where you might need to use your notes, hexagon. Remember the hexaldoses have hexagon geometry. What monosaccharide has pentagon geometry? None of these. Which one does? Fructose, because it's a ketose. So we've got 2 hexagons here. So both of these molecules look like that. Well, how come the enzyme that breaks down maltose, which would be maltase, won't break down lactose? In other words, somebody's sensitive to dairy products. They're lactose intolerant because they don't have the enzyme lactase. Why doesn't their body just use the enzyme maltase to break down the lactose? Because of the specificity. It's just as specific as the freaking keys, guys. Just like keys. They all look the same. But there are 4 different ones here. Specificity. Enzymes, substrates, lock-in keys, active site of an enzyme. Sometimes proteins have a 4th structure called the quaternary. And the quaternary structure, you probably remember, but it's when you have multiple polypeptides. So imagine 2 or 3 or 4 polypeptides, each with a primary structure, a secondary structure, a tertiary structure. And then those 4 polypeptides are held together into a huge globular configuration. The notes give you, I think anyway, they do, the last line, the terms to describe these most complex proteins that have the quaternary structure, dimer, trimer, tetramer, indicating how many peptides they have. This picture, straight from your book, shows us hemoglobin. Up here, they're representing the primary structure. So what amino acid is number 1? Maybe it's glycine, maybe it's isoleucine, maybe it's tryptophan, I don't know. But it's one of the 20. So what amino acid is in each position. Then we get some coiling or some folding, alpha helix, beta pleated sheet. And the coiled and folded chain takes on some more complex folding. And in the case of hemoglobin, we end up with 4 polypeptides all together. And you certainly talked about hemoglobin in biology. It's the one everybody always uses, but let's talk about it again because it's so extremely important. Of course, in your red blood cells, when you take the histology practical, you're not going to call them red blood cells, are you? You're going to call them erythrocytes. What percentage of your cells are erythrocytes? 94%? And what's the other 6%?
Well, is it
0.14% are the white cells, and the 6% are the platelets or thrombocytes.